Right off the bat, we have a 13,200 pound force pointing upward. So we're going to go straight up to a value of 13,200. And just like before, this distributed load is going to cause it to fall. So it's going to keep dropping. The shear will reach 0 in the middle. But here's where the change happens. If you look, if you follow this point load down, when you get to this point, there's suddenly a massive drop of 8,000. So wherever we got to here, we're going to go down another 8,000. And then it's going to continue following the trend it had before. And then at the end, we know it's going to go up by 18,800. So that means I know it's going to be at minus 18,800. When it gets down here, I know that because it's going to jump by that amount to get back to 0 at the end. There's that massive jump, and it creates like a trapezoid shape here instead of a triangle like we had before. So now we have a non-uniform shear diagram, and you can very clearly see that there's more shear down here on the right side of the beam than there is on the left side. So it's more likely to fail in shear over here this time, and that makes sense because there's like this puncturing due to this extra 8,000 pound force. So again, we want to find all the areas here, and right off the bat, I think I'm just going to separate it into 3 shapes this time. So we're going to call this shape 1, shape 2, and shape 3. And so I need area 1, area 2, area 3. So this is where it gets a little bit trickier because when we just had a uniform distributed load with no extra point load, we knew that this line intersected here right in the center of the beam. That's where it had 0 shear. And that made it clear that this was a 10-foot length for the first triangle. But that's not the case here because this extra load messed things up. So we have to figure out where this intersects this 0 point. And so we can set up a line in the form of y equals mx plus b. And we want that y to be 0 in this case. The m is the slope, which is negative 1,200. And the b is the y-intercept, which is the 13,200. And so if we move this stuff over, we have 1200x equals 13,200. And so x, which is the distance until it intersects 0 right there, is equal to 13,200 divided by 1,200. And that gives us 11 feet. So it's close to what it used to be, but instead of right here in the center, it's actually shifted 1 to the right. And so that means this distance is 11 feet. I'm going to mark that. And that means if this load happened at 17 feet and this is 11 feet, so that means this distance is 6 feet. So I'm also going to add that in here. This is a 6-foot distance. And this last bit is 3 feet. So this is not to scale, but you have to do this extra step here to figure out where that intersection point happened due to the fact that this external load has shifted things.